So 4.7 optimization problems. Here is where we put basically all of the pieces together in an application when we are looking for the first derivative, the second derivative. In some cases, we need to use the first derivatives test. Second derivatives test could be easier. It kind of depends. Or you could use the EVT, the extreme value theorem, where you just test the endpoints if that particular problem has endpoints against the relative maxes and min. So it just kind of depends on the problem. In the do now, I'm hoping you've done it already. If not, then you should be trying this. It says finding relative minimum and maximum values. One way is the relative min or maximum value are found by using the critical values and testing them with the first derivatives test, in which you can see if a function changes from increasing to decreasing or vice versa to determine if you have a relative max or min. A second way is to take the relative max or min values, or to find the relative max and min values, is using the critical numbers and then testing in the second derivatives test, in which you check for concavity at each point. So if the second derivative is positive and the first derivative was 0, that means it was concave up, so it must have been a relative minimum there. And if it was the second derivative was negative, then the function must have been concave down at that critical number, so that must have been a relative maximum. Another way is if the domain is restricted, it has endpoints. So the extreme values may happen at the endpoint. So you always have to determine that, especially in optimization problems. The best way to actually just do is to jump in and try some problems. Hopefully in pre-calc, you've done something, at least set up the equation for something like, finding the best or the surface area of a box that's open on the top, or it could be completely covered, or a wrapping paper problem. These are all kind of related to that. So let's try and put some calculus into it. It's saying here, for example 1, a manufacturer wants to design an open box having a square base. So here, the two sides of the base are both x, and a surface area of 75 inches, as shown here in the figure. I forgot to add that. What dimensions will produce a box with maximum volume? So a couple of things. First of all, it's always a good idea. You have a drawing here already, but to kind of organize your thoughts. And the key is you need to write down what it is I'm optimizing. In this case, it's optimizing volume. It's talking about surface area in the problem, but it's not what we're trying to maximize. So we need to just write down in words, okay, I need to maximize volume. I'm going to write the volume formula for the box. Now, the surface area serves then as a constraint then. So the constraint is the surface area. You take the area of the base, which is only 1 because it's open at the top, right? And I know that that's going to be 75. So the area of the base was x squared, and then it has four lateral surfaces, the front, the back, and the two sides. And each of those are x by h. So here, let's see here. Up here, that's an h, and here is an x. So this front is xh, the side is also xh, the back is xh, and the left side here is xh as well. There's 4 of those of that particular size, so that's where I got the formula for the surface area, right? And I know that that's going to be 75. So this is my constraint. So now my next job is to write an optimization function, but we want to do it in just one variable. So that's where the constraint comes in. So we're going to rewrite the optimization equation in one variable other than what we're optimizing. So the volume is going to be there. But that means I'm going to solve the constraint, in this case, which was the surface area, for one of the variables. In this case, it seems the simplest just to solve for h. So I took this equation right here and just solved for h by subtracting both sides by x squared and then dividing both sides by 4x. And then we are going to substitute that in for h in the volume formula. So I want to manipulate the volume formula because that is what I'm trying to optimize. Once I have done that, substituted that in and maybe simplified a little bit. If I'm doing this by hand, later on we're going to do some with a calculator, but if I'm then I would just leave it. There's no need to manipulate it any further. But because I'm going to do this without a calculator, I'm then going to just do a little bit of cleaning up. A set of x's cancels out here, like these. This becomes a 1 there. And I can distribute the x and divide each term by 4. It seems simpler in that form because then I can just use the power rule for each of those terms. So that's what we're going to do. So finding the extremas does a couple of things we have to check for. We have to make sure if there are actually any natural endpoints to this. In this particular case, if, for example, x was equal to 0, we would have no box. And the other option is if x is equal to the square root of 75, because that means the whole surface area was used for the base, or none of the surface area was used to the base. So that means that it has an interval from 0 to the square root of 75, or if you want to be fancy, you could do 5 root 3. But in this particular case, it doesn't actually have endpoints there. So we always keep that in the back of our minds. Like, what would the extremas be? Does it have endpoints? In this case, no, we don't get a box either way at the endpoints there. All right, so let's look. We are then going to take the derivative of the volume because that's what I want to maximize. And to find the relative maxes and mins, you take the derivative and set equal to 0. That's the whole purpose of taking the derivative. So I found the derivative using the power rule, and then I make sure, if this is a free response, make sure you justify. You write v prime is equal to 0 when, and then actually set the other side equal to 0. Sometimes, let's say you made an error in the function itself, you can get a point for just writing v, recognizing that v prime has to equal 0. So it would be nice to eke out an extra point. Let's say you made a mistake, right? And then you set it equal to 0 and solve for x. So here we got x is equal to positive and negative 5. Now, I will only use the positive 5 because we're in the interval from 0 to 5 root 3. So the negative 5 is not there. And also, you can't really have a negative length of a box or side of a box. So that wouldn't make any sense even if I just used common sense instead. So now that we've found that, we take that value and, let's see here, use the second derivatives test to make sure that it's a maximum. So I'm going to take, and I'm using the second derivatives test to test for it being a maximum because it didn't have any endpoints. Otherwise, I would be testing the endpoints with that critical number in the original function to see which one gave me the highest or the smallest number, depending on what I wanted. But in this case, I know that it's not going to happen at the endpoints, so I'm just ensuring that I know, oh yeah, when I substitute that into my 5 into the second derivative, if I get a negative, it means the function is concave down there. And if the function is concave down there, it's going to have a relative maximum on that point here. So that's what we can conclude here. V of x has a maximum at x is equal to 5 since v prime of 5 is equal to 0. So the first derivative is equal to 0, but the second derivative is negative. So that would be my justification there. And then I know that the dimensions of this particular box would have to be 5 by 5 for the base, and then the height, what's left for the height is then 5 halves, I think. And the way that I figured that out is just, you could put it in the surface area, right? So you have 75 is equal to, the base would be 5, so that's 25 plus 4 times 5 times height. So that's what we're looking for here. So that's going to give me 50 is equal to 20h, and then h ends up being 5 over 2. And that's where I got the 5 tab. Or if you're around and write 2.5, that also works. So that's basically using derivatives for something I think you may have done in pre-calc already. But if you haven't, hey, here's the way you can now use calculus to do that particular problem.